Alright, so in the last video, we went over the basics of how to solve non-homogeneous differential equations. And it's basically, you find the complementary solution, which is like what we've been doing earlier. But now we also need to find a particular solution to add it to. And, well, let me define this complementary part, this YC, because it's what we've been doing earlier. It would be like AY double prime plus BY prime plus CY equals 0. That is a homogeneous part, and we'd factor it out like AR squared plus BR plus C. And we'd factor it out. We'd get complex roots, repeated roots, distinct roots, one of the three, and we'd use the correct formula, etc. And we'd get our complementary solution. But non-homogeneous differential equations equals some f of x, some function of x. So, what we end up doing is solving it as we normally would, just pretend this is 0. We'd factor it out, we get our complementary solution, and then we make a guess of what y of p would be. And, well, you'll see soon enough that you actually need y of c first before you can fully guess what y of p's form will be. It's best to just show you an example. So let's jump right into it. So r squared minus 16r equals 0. We just factor this out, and we get r times r minus 16. We get r equals 0, r equals 16. So we get distinct roots. Distinct roots. And that is of the form c1 e to r1 t plus x plus c2 e to the r2 x. And while we plug those in, we get yc equals c1 e to the 0 plus c2 e to the 16x. And this e to the 0 is interesting, because it turns out this is just a constant, just c1. And, well, that's our y of c part. That's part 1. But now we need our yp. So our guess, we'll just say generally, we know that e to the 4x will stay the same, and we'll have some constant in front. And our guess is just y. Plus some constant b times x, plus some constant c. Now, we know it will be somewhat of this form. Some constants plus a constant times x plus a constant times e to the 4x. Now, if this final equation doesn't have an x part of it, well then b would just equal 0 and problem solved. But one thing I realized is our final solution is y, and it equals the particular solution plus the complementary solution. And we have this constant c plus another constant right here. This is no longer a function of e to the x, because it's e to the 0, and that always equals 1. So what happens if we add c to the 1? Well, c1 plus c. Constant plus a constant is still a constant. So it doesn't change anything. So we actually need to multiply this by x. But then again, well, we add them together, we get b to the x plus c to the x. Well, that's just b plus c times x, and well, a constant plus a constant is still a constant. So we actually need to multiply this by x as well. And if this was 16x, then we'd also need to multiply this too. But now we see that there's nothing repeated. And normally we'll do this in future videos, but this is just like a boot camp, just practicing guessing. Normally we derive this a few times, plug it in, get a, b, and c, then add it to yc for our final solution. And if we had initial conditions, then we'd solve for c1 and c2 as well. But let's continue on over here. It'll make more sense as we go along. So this, we just pretend it equals 0, so r squared plus 4 equals 0, and we get r equals plus or minus the square root of negative 4. So r equals plus or minus 2i. So we have complex roots. No problem, we've done that before. So we have yc equals e to the alpha t times c1 cosine of beta t plus c2 sine of beta t. And, well, this alpha right here is 0. So we actually just have 1 times this, so y of c is just, this cancels out to just 1. So we get c1 cosine of, and beta's 2, so 2t, plus c2 sine of 2t. So this is our complementary solution. But we also need our particular part. So we make a guess, and let's just say it's a sine of 2x. Now let's just derive this a few times. We'd get 2 times a times cosine of 2x, and then we do it again, we get 2 times a times negative sine of 2x, and it just keeps going on, and it repeats with more and more 2's, but one thing I realize is this inside, the 2x, doesn't change. And another thing I realize is, well, we have a cosine of x, and the tricky part about this is our particular solution also needs to account for these derivatives that have cosine in it. So we also need to add a constant like beta cosine of 2x just to account for that. Now, if our final solution doesn't have like a cosine part, then beta would just equal 0, and it's just what we had earlier. But in order to account for these derivatives that switch between sine and cosine, we need to add a beta cosine of 2x part. And this inside part, basically if you have a chain rule, you just keep it as is. But this inside part will stay the same, but we have these general constants. Because, you know, it would be a, or it could be 2a or 4a, anything times 2. But, so we get y of p equals a sine of 2x plus b cosine of 2x. But there's another problem here. That's exactly what we have down here. c1 and c2, a and b. Add those together. I mean, a constant plus a constant is still a constant. So we actually need to multiply this whole thing by another x. So yp ends up being ax sine of 2x plus bx cosine of 2x. And that is our guess. Then you derive this, you'd plug it into this equation, you'd solve for a and b, add them together, and you get your final solution. Now let's do one more. So we treat this as homogeneous, we set a equal to 0, and we just factor out, so r squared minus 4r plus 5. And, well, does this factor nicely? 1 and 5? Yeah, we can do that. So r squared plus r minus 5r plus 5. r and r plus 1, negative 5 and r plus 1. We get r equals negative 1, r equals 5. So we have distinct roots. So we get yc equals some form of c1 e to the negative x plus c2 e to the 5x. Right? Let me just make sure I did this correctly. r squared minus 4r plus 5. 1 and 5, so negative 5, 1. I think I may have written down the example I was going to do wrong. One sec. Okay, I was planning on showing something else, but we'll just run with it. So, negative x, 5x, constants. Now we do this, and what we have e to the 2x times cosine of x. We make our guess, but we also need to account for sine of x. If we derive this, we'll get like 2e to the 2x times, well, negative sine of x. When we derive it again, we get something of cosine of x, then sine of x. I mean, you can't read that, but you know what I mean. But the thing is, this only accounts for cosine of x. We can't multiply this by a constant, a or b, and get sine of x. So we also need to add e to the 2x times sine of x. So our particular solution is e to the 2x, well, a times e to the 2x cosine of x plus b e to the 2x times sine of x. Now, if this was a complex root problem, we'll just pretend something like that. Oh no, we have something like r equals plus or minus 3i. Then we'd get alpha equals 0. And we get, well, yc equals e to the 0 times x times c1 cosine of 3t. We'll just say this is regular I, so cosine of t plus c2 sine of t. And, well, this e to the 0 is 1, so it cancels out. And we're just left with let's say it's alpha equals 2. Stick with me. We get e to the 2x times all that. And we factor that out, and we get some constant, like a in C1, times e to the 2x, e to the 2x times cosine of t, or x. And that's exactly what we have. So we'd actually need to multiply this all by x so it doesn't repeat. I butchered it in the end, but hopefully that makes sense.